We will come back and we will start this 10th lecture, and we will continue our discussion on radical chain polymerization. And in this lecture, this 10th lecture, I will try to complete the discussion on the different type of radical initiator which we began in the last lecture, and briefly talk about the initiator efficiency, and then go into the mechanism and kinetics of radical polymerization, which will include the dependence of polymerization rate on initial initiator concentration as well as monomer concentration, and we will talk about kinetic chain length and molecular weight of the polymers produced in chain polymerization, in this case radical chain polymerization, and if we will try and see whether if time permits we can or we will start the chain transfer. And we talked about we are actually talking about different types of initiator which can be used or which are typically used in radical chain polymerization, and we talked about different types of initiators which can be used or which can be utilized. For example, we talked about thermal initiator, where by applying heat we can dissociate homolytically a set of molecules, a different type of molecules, for example AIBN and benzoyl peroxide, which we can use for radical chain polymerization as initiator. We are talking about other methods of chain initiation, radical generation, and we started a discussion around redox initiator, and in the redox is basically reducing agent and oxidizing agents, and we gave example of peroxides and reducing agents like ferrous iron, and we also talked about the peroxides and amine, and then we start today with more options of redox initiator. So, let us continue this redox initiator discussion. We can take we talked about this example of benzoyl peroxide and diethylamine in the last class, and we also showed the values of Kd, and we found that we have seen that Kd is much higher for this redox reaction, which means redox reaction can be conducted. The radical polymerization, where the radical is generated by a redox reaction, can be done at lower temperature, including a subambient temperature, compared to the thermal initiator. The third type of initiator, redox initiator, could be inorganic reductants plus inorganic oxidants. Which gives rise to the other examples could be persulfate plus diamine. A very common or very popular use of this combination is typically used for making polyacrylamide gels, which is a combination of ammonium persulfate APS and TMED. This reaction is very common and done in biochemical laboratory for making polyacrylamide gel for polyacrylamide gel electrophoresis. TMED is NN N-dash N-dash, it is basically a diamine, tetramethyl ethylene diamine So, the combination of persulfate plus diamine gives the radical. Now, we talked about thermal initiator, we now learned about the redox initiator. The other examples or other types where you can utilize is photochemical initiator. Photochemical initiator or photo initiator in short. For example, here you can use aromatic ketones. In this case, on photo, these molecules can absorb photon and go to a higher excited state, which can actually dissociate to form a couple of radical. Now, this can also react with or photosensitize another molecule. For example, if I have from here, if I have another molecules, and if AR is pH, so here what we are showing here, that you have a aromatic ketone which on photoradiation it absorbs photons and go to a higher excited state, which by itself it can break or dissociate homolytically forming radicals, or it can actually photosensitize another compound and go to a and make a complex in excited state, which further can dissociate producing radicals. For example, if you have diphenyl ketone, you react with a molecule like this, form, and this decomposes, and this can initiate a chain polymerization. Simple, this AIBN type molecule also can absorb photon and break into two radicals, and most commercially used radical initiators are like benzoins. For example, I have molecule like this, or you can have say ketones, benzyl ketones, where you have structure of that like this. These are the main type of photo initiator or photochemical initiator used in commercial applications. Now, the advantage of these photochemical reactions or photochemical initiator is that you can do your polymerization reactions locally. If you have a if you have a reaction mixture, and if you can partition or you can cover some part with a opaque material, then the part which is exposed to the photons or light, that part will get polymerization. So, it is very useful applications like film, where you can cover the part of the film and you can keep part of the film uncovered, where if you shine light, that part will get polymerized, leaving the part which is covered as unpolymerized medium. So, this photo polymerization method or the radical polymerization by photo initiator sometimes can be used as an advantage. This can be used or used to apply or used to make polymers in a local or in a whatever targeted part. The other type of initiator is like initiation by high energy radiation, like gamma ray or X-ray. Now, these are very high energy. So, when it reacts with say some organic molecule, it can form a radical cation and eject a electron, and this radical cation can dissociate into a radical and a cation, which can capture this electron and form another radical. There may be another possibility where on this high energy radiation can capture a electron and form a radical anion, and this radical anion can dissociate into a radical anion, and which again gives up a electron to form a radical. So, using very high energy radiation sources, we can apply and we can generate a radical which can initiate the radical polymerization reaction. The other type of initiation is the thermally induced self initiation. That means, the monomer itself on thermal or on heating can give rise to or can generate radical, but this is not a very common way of generating radical. This has been proved only for the case of styrene, and this is the mechanism which is proposed for thermally induced self initiation of styrene, whereas two styrene molecules by Diels-Alder coupling first get dimerized, and then this dimerized styrene molecule can react with a third styrene, which abstract a hydrogen atom and forming two radicals which can individually initiate the chain polymers. This is the proposed mechanism for styrene, which have been proved, but this thermally induced self initiation is not a very common, and it is only shown for styrene. So, this is very specific case for styrene. The other types there are few other special type or very small applications of other types of radical generation or other types of initiator. For example, there are electrochemical initiator. If you have a salt of carboxylic acids and present in electrochemical cell, then in anode this carboxylic acid salt can get ionized, oxidized to form a radical. So, for example, if I write this, it can give up electron in anode and can produce radical in a electrolysis. If you want to do a electrochemical polymerization, electrochemical radical polymerization, you can use this technique to start the polymerization. So, by this time we now know different types of initiation possibilities. That means, different types of molecules which can be used as initiator to generate radical in the reaction medium, and not only the molecule, but the ways they can produce radical, for example, by thermal, by photo, or by electrochemical we just talked about, or the radical can be generated by very high energy radiations like gamma ray or X-ray. Now, if you talk about if all the radicals which are produced, do they all react or do they initiate a polymerization? Not always. The fraction of the radicals which are produced by homolytic cleavage or by redox reaction of the initiator molecules, they all, not 100% of those, starts a chain polymerization, or they initiate chain polymerization, part of which are get lost, and the fraction of which of the radicals generated during this initiation process which start the initiation reaction is termed as initiator efficiency, and is typically the initiator efficiencies lie around say 0.3 to 0.8, which means that the among all the radicals which are generated, around 30% to 80% of the radicals actually generate or initiate a chain polymers. What happened to rest of the radicals which do not generate or initiate a chain polymers? They get destroyed to form dead molecules. For example, if you take AIBN, if we have seen that AIBN on dissociating to this species, now they can again recombine by reacting with themselves and form this molecule. In this case, part of the radicals which were generated by homolytic cleavage of AIBN, they are getting destroyed, in the sense they are becoming inefficient or dead non-radical species by reacting with themselves. So, part of which are lost. A propagating chain which are expressed as Mn dot can also react with this a radical, primary radical, and form a dead molecule. So, by these are a few ways where the radicals which got generated by the initiator molecules, they get destroyed and form non-reactive molecules. Other examples, like if we take a benzoyl peroxide example, and we talk about induced decomposition of initiator. If I have a propagating radical, now if I give example of benzoyl peroxide, the propagating radical can react with the initiator molecules and forming another radical. Now, these molecules in normal case were supposed to generate two radicals, but in this case on reacting with a chain, propagating chain, it is only producing one radical. So, the efficiency of the radical initiator is decreased, and not only that, they can undergo these radicals which are produced initially, they can undergo lots of side reaction and get destroyed or get formed into non-radical species. For example, again take the example of benzoyl peroxide. It get dissociated to this. Now, two of these can react and form CO2. This can react with monomer, and there are several side reaction possible with this, and by this sort of side reaction, this all can undergo phi dot plus CO2. Now, this can further undergo several side reactions. So, if there was no side reaction, the amount of radicals it were generating, now it has reduced because of these so many side reactions, or in other words, all the radicals which are getting generated by homolytic cleavage of this benzoyl peroxide, they are not participating or they are not initiating a chain, which means that is that they are getting lost in doing non-polymerization reaction. So, that is the reason that not 100% initiator is efficient, a part of which like 30 to 80% of the radicals generated initially, they actually initiate a polymerization reaction. So, we have talked about different initiator and different way of different types of initiator and how and the efficiency of initiator. Now, let us talk about kinetics of radical polymerization. As we know, the first step is initiation. Now, initiation consists of two steps. One, initiator molecules produce two radical species. This is the initiating radical, or it is called the primary radical. This primary radical react with a monomer, Rm dot, we are just for short we are writing M1 dot here. This is chain initiating radical or species. So, these are the initiation step is actually consists of two sub steps 1 and 2, and then this chain initiating radical react with another monomer M1 dot plus M2 dot. This again react with form M3 dot, M2 dot is RMM dot, this is RM M dot, and so on. This you can write many steps, and in general I can write dot. Now, these steps are part of propagation. So, we had initiation in earlier page. Now we know propagation, and this can undergo termination. Third step, we will talk to that in a minute. Now, rate of polymerization RP is given by rate of consumption of monomers. Now, it is assuming that the monomers which are getting consumed, they are reacting and forming polymerization, they are becoming part of polymerization. Now, what are the stages or what are the reactions the monomer is getting consumed? We talked about in the initiation reaction. Here the monomer is getting consumed. So, I write initiator rate there and plus all these steps. So, if I write these steps RP1, RP2, RPN and so on. So, RP1 plus RP2 plus RP3 plus RN N plus so on. Now, because this is very small amount of monomer get consumed in the initiation reaction, we can ignore this and we can write RP as a sum of all these propagating steps. Now, if I write rate constant for this individual step as Kp1, Kp2, Kp1n, then what is the individual space? Rp1 is given by Kp1 m1 dot m plus R2 is given by Kp2 m2 dot m plus so on, and this Rpn is given by Kpn mn dot m. Now, it is very difficult. If you want to find out this, you have to know all these rate constant Kp1, Kp2, Kpn, Kp3, Kp4 and all these things. That is practically impossible. So, what is assumed that all these rate constant for all these propagating reactions, they are same. It is similar to the assumption we made for step growth polymerization, the assumption of equal reactivity of the functional group. So, remember we talked about in step polymerization that the reactivity of the functional group present at the end of a oligomeric chain or a polymeric chain does not depends on what is present in the other side, whether the other group is reacted or what is the length of the oligomer. Similarly, in this case the reactivity of this radical does not depend, we are assuming that it does not depend on the size of the molecules, whether it is a M1, M2 or, because this system is large and we know that it has been experimentally proved also that the rate constants become very, all become same as soon as they become this chain containing 2 to 3 monomers. As long as this chain contains 2 to 3 monomers, the rates, all the rates become, all the rate constants become equal. So, that is the assumption we are making, that all these rate constants are equal, and so we can write all the rate constant as Kp, and m is there in everywhere. So, I can remind, and also we are write the summation of mi dot. Okay. So, these are all are same, Kp1, Kp2, Kpn, these are all same. So, I can take it out, and then m is present in everywhere. So, m is also taken out, and a summation of all the other terms m1 dot, m2 dot, m3 dot, m1 dot. So, this is I dot. So, this term I can simply write Kp m m dot. I am just writing this m dot. So, m dot is this is the summation of the concentration of all the radicals present, all the propagating radicals present in the reaction medium. So, this Rp now given by Kp, rate constant for all those individual steps, monomer concentration, and this is the summation of the concentration of all the propagating radicals of the all the chain radicals. Okay. This is the sum of all those things. Now, experimentally, or this is an unknown quantity, we cannot, it is very difficult to measure this quantity experimentally. So, how do you get this rate of polymerization? We assume a steady state where now immediately after the reaction starts, the change in total radical concentration becomes 0 with time, which means that the radicals are consumed at the same rate as they are getting produced. Now, radicals get produced in the initiation reaction and they get destroyed in the termination reaction, which we just going to talk in a minute. So, as soon as the reaction start, within a very short period of time, the rate of initiation becomes same as rate of termination. As a result, the concentration of this total radical species, radical propagating radical become constant during the entire polymerization reaction, and that is not very unusual, because when we do the kinetics of the first reactions with having intermediates, then we always assume steady state and we do the kinetics in that way. So, in a steady state, the rate of initiation is equals to rate of termination. Now, what is the rate of termination? We talk about termination step now. Now, how this in radical Mn dot they can get terminated? If I talk about that same structure, take out that same simple monomer. Now, how this can get terminated? They can get terminated reacting with the same molecule, and by coupling reaction they can so that is K termination by coupling. This is a coupling process. See, if I write this as Mn dot, this is a M dot, then this will be Mn plus M. Now, they can get terminated by other type of reaction, disproportionation reaction as well. Disproportionation. Two of these for example, if I talk about methyl methacrylate, like this is can form two different species. So, if I write n dot here and this is m dot and this reaction is K termination by disproportionation, then gives again Mn plus Mm. Okay. So, here the molecular weight on termination, the molecular weight does not change, ignoring the difference of 2 hydrogen here between these two. So, in this case the molecular weight remain unchanged, it becomes the dead polymers have same as the size of the reacting polymer, where in the earlier case it is the length of the final terminated chain is the summation of the size of the two reacting species. Now, in general we can write Mn dot plus mm dot gives right Kt gives rise to dead polymer. So, if I write this, then it in general it takes care of both the coupling reaction and the initiation reaction. In both cases these two propagating radical reacting and forming dead polymer. So, what is the rate of this termination step is given by Kt m dot square, because it is a bimolecular reaction. So, now this is again the m dot is the summation of concentration of the all the propagating radical. So, now I write this rate of termination is, we now got that it is a bimolecular reaction. So, Kt multiplied by m dot square. So, from that we can find the m dot as Ri by Kt to the power half. Okay. Now, in some cases, in some text they follow that RT is rate of termination is twice Kt m dot square. Now, this term twice is introduced in some text. This twice is introduced because that one termination reaction is effective in bringing the termination of two radical. So, these two terms we introduce. Now, if it is up to you whether you want to write 2 or you do not want to write 2, but if you write 2 here, then similarly when in initiation reaction homolytic cleavage gives up 2 radicals, you have to write 2 as well. So, that these 2 cancel out. Okay. And if you choose not to write 2, then during the initiation reaction also you have to choose not to write 2 in this case. We will come back that initiation reaction rate of initiation again when you write the expression for Ri rate of initiation. So, Rp rate of polymerization we have deduced earlier m dot, which will now become m Ri by Kt. Now, let us write 2 here, let us follow this convention. So, I write 2 and this is what the rate of polymerization is. So, we have to know Ri. Now, Ri is, this is for thermal initiation. So, how do I write the Ri? We write this is Kd I. Now, again because this produced and we are following that we should write 2 here during the termination rate. So, here also we write 2 and also with our knowledge that all the radicals which are generated by the homolytic cleavage of the initiator molecule, they do not react or they do not initiate the chain polymerization. The fraction of the radicals which generated here, some of them actually initiate the radical polymerization, and so we multiplied in the term F, which is the efficiency. So, this would give the total expression for the rate of initiation, rate constant of the dissociation, initiator concentration, this is the efficiency of initiator, and 2 we are writing because we are following the same conventions 2 here. And the logic is that because one initiator molecule is giving up 2 radicals which are initiating 2 chains, so we are writing 2 here. Now, if we go back and look at this, compare this initiation reaction which we wrote earlier, and you can argue that we are not talking about or we are not taking this reaction in the consideration when we determining Ri. Now, the fact that this is the very first reaction, this as well as all the propagating reactions, they are very fast compared to the initial dissociation reaction of the initiator molecule into 2 radicals. So, the initiation reaction actually depend on the first step, not at all on the second step. So, when we are considering rate of initiation, we are only taking or only considering this Kd, not the Ki. Okay. So, that is clear that in spite of there having 2 step in the initiation process, we are taking the slowest step, which is basically the rate determining step for the initiation process. So, finally, let us talk about the final expression for rate of polymerization. This is rate of polymerization Rp. Now, this is for thermal initiator, it is given by Rp is given by Kt Kp m Ri, Ri is twice F Kd I twice Kt half, these 2 cancels out. So, Kp m F Kd I Kt to the power half. Okay. Now, this is for thermal initiator. What is it would look like for a redox initiator? For redox initiator is rate of initiator is Kd concentration of reductant oxidant. So, Rp would be Kp m Kd oxidant by reductant concentration by twice Kt to the power half. For a photochemical initiation or photo initiation, Ri is twice phi I A. I A is the intensity of the radiation and phi is the quantum yield for initiation, is similar to efficiency F for thermal initiation. This phi is the quantum yield for initiation. So, for this type of initiation we can write Rp is m phi I A by k T half. So, we talked about the most common rate expression for rate of polymerization, whether it is initiated by thermal initiator or redox initiator or by photochemical initiation. These are the most common route of initiating a radical polymerization. So, we know the rate expressions for the rate of polymerization. Now, let us go back and look at this thermal initiator, which is the most common. Rp is given by this, which means rate of polymerization is directly proportional to the concentration of monomer, and it is actually directly proportional to the square root of the concentration of initiator. So, Rp is proportional to the concentration of monomer and it is proportional to initiator concentration. So, if you increase the concentration during a radical polymerization, then you know the rate will increase, but of course, at the proportional to the square root of the initiator concentration, and if you increase the monomer concentration, then the rate will be increasing, rate of polymerization would be increasing in as a directly proportional. So, if you plot, and this has been shown experimentally, if I have this plot Rp, rate of polymerization with I to the power half square root of I, it gives a straight line so as this. Now, sometimes experimentally it is found that it is not directly proportional to the power for initiator, it could be more than 1, so like 3/2 some cases. Experimentally you might find out, or some cases it might be even lower. Now, that indicates that see if the rate of polymerization dependent not directly, not to the power 1, but more than 1, say like 3/1.5, which means that this monomer also taking part in generating radicals, and that might have in few cases where the monomer can take part in homolytic cleavage and generate radical, or it can react with some other molecule, initiator molecules, and produce a radical. So, if the monomer itself take part in the initiation reaction, then there is another terms comes. So, you get a half here, an additional half. So, it basically comes 1.5. Similarly, if you see that this is not following, this actually following even less than that, which means that some of the initiators which are produced, they are actually even the some of the radicals which are produced by from the initiator molecules, they are not taking part. So, efficiency actually came down during a reaction. So, which also means that as the reaction progresses, both the concentration of monomer and the initiator comes down, which means as the reaction progresses with time, the rate of polymerization also comes down. But there is a special case at the end of the reaction, if the monomer concentration is very high, which we will talk about in the later lecture. So, again to form, you can write the now, if you go back this expression, besides this term, this concentration term, monomers and the concentration of monomer and concentration of initiator, these are also will determine your rate of polymerization. So, and which will depend upon the temperature. If you increase the temperature, then depending how it is affecting the values of Kd, Kt and Rp, the rate will vary. Now, we will come in a later lecture what is the effect of temperature on a rate of polymerization. Now, let us talk about a molecular weight in radical shell polymerization. Now, before we come back to discussion on molecular weight, we will define a term kinetic chain length nu, which is average number of monomers polymerized per each radical, which initiate a polymer chain. So, it is the average number of monomers which polymerize per radical which actually polymerize, which actually initiate the polymerization, not the as I said that some of the radicals get consumed by side reactions or some other reactions which do not initiate polymer chain. So, this is the average number of monomers polymerized per radicals which initiate a polymer chain. So, it is, how can you write in simple term, it is rate of polymerization divided by rate of termination, or as steady state assumption it is same as the radius of rate of initiation. So, we can write nu as kpm from your the last expressions which we derived in the last few pages. We can write this as well. And if we consider only the case of thermal initiator, then nu is again Rp by Ri Kpm So, nu is the average number of monomers which is getting polymerized per radicals. You should consider the radicals which are only those radicals which are initiating a polymer chain. So, what would be the average molecular? What is the relation between the average degrees of polymerization with nu? How these are related? Average degrees of polymerization and this nu. If the termination is done by coupling, then Mn would be, Xn bar would be, the average degrees of polymerization would be twice nu. Nu is the average number of monomers consumed in this chain. Okay. So, the degrees of polymerization will be summation of this plus this, and we are talking about average. So, it is 2 nu. If it is gets terminated by the disproportionation reactions we showed earlier, then average degrees of polymerization is nu, because the number of monomers, average number of monomers per radical is the size of this chain, and we know that Xn is Mw, Mn bar is M0 Xn bar. So, which means if the kinetic chain length, there is kinetic chain length which basically a number of radicals, number of monomers which consumed per radical. So, you have a radical propagating chain and if another propagating chain, if they are terminated by a coupling reaction, then you have twice nu is the molecular weight, average molecular weight, degrees of polymerization. Whereas, if they are terminated by disproportionate reactions, then the average degrees of polymerization would be equals to the kinetic chain length nu. And how do you determine what are the number of molecules? If they are terminated by coupling reaction, then every dead chain would have 2 species from the initiator molecule, the fragments, residual fragment from initiator molecule, and if they are terminated by disproportionation, then they will have 1 residue from the initiator molecules. Now, what we will do in the next lecture, we will continue from this and talk about termination reactions or transfer reactions.